Hi, welcome back to Codex. Today's speaker is Tim Kunisky from Johns Hopkins. He's an expert in the mathematics of data science, and today he'll tell us about computational hardness of certain graph problems. Take it away, Tim.
All right, great. So thanks for the invitation to present. And yeah, so I'm going to talk about recent work together with Shifan Yu, who's a wonderful grad student at Yale, where I was until just recently. Um, so so I'll start out kind of introducing the main topics, maybe giving you some motivation. So I want to think about a class of problems, of computational problems, computational tasks, which are attached to optimization problems. So my model problem, hopefully this will be a good example for this audience, will be max cut in a graph, and maybe some other graph problems in a minute. Um, so usually when we talk about solving max cut, right, we think about the problem. So you're given the instance is the graph, right? And the algorithm's task is to output a cut that is large, right? That cuts many edges, a partition that cuts many edges. I want to think about kind of the converse task to this, which I'll call certification, where you output not a cut, but you output a number, and your algorithm has to promise that that number is always an upper bound on the size of the maximum cut or the size of all possible cuts. And so this is a natural sort of task to ask about. You can think about one reason that you might want to do this as if you only have a heuristic search procedure, right, that doesn't come with any guarantees, but you want some guarantees, you can run your heuristic. It'll output a cut of, cutting 10 edges or something. And then you'll run the certification algorithm and it'll say the best cut cuts at most 12. And maybe that'll be good because you're close to the truth. Or maybe it'll say the best cut cuts, at most 100. And that's not so good because it seems like there's lots of room to improve. Right? So another way to view this from a kind of more theoretical kind of computer scientist's perspective is that this kind of algorithm has to prove in some sense that there is no large cut. And so this, in the context of satisfiability and things like that, is of interest there. And so this kind of problem, hopefully it's intuitive, can be a lot harder than just looking for one good cut, because instead of just outputting this one object, you have to make a claim, you have to kind of quantify over all possible cuts. And so what I'll talk about in this talk is how hard some problems of this kind are in the average case, so over random graphs. And so somehow, people had thought about this, including myself before, for lots of different graph problems. So these are some examples. And the thing that I'd like to emphasize for now about this work is that what we're after is really a general way to think about these problems, right? So some sort of framework for average case lower bounds for these kinds of problems, specifically over graphs, that can somehow handle all of these problems at once or in some unified way. So in particular, the kind of random graph that I'll talk about, and as we'll see, this kind of gives rise to some interesting structure in these computational problems, is a uniformly random regular graph. So let's say there's some number d, maybe 3 or 4, or in the limit as d goes to infinity, and we'll pick uniformly from the regular graphs on a certain number of vertices where every vertex has that degree. Right, so let's talk about the usual situation when we ask how do these quantities, just the actual values of these optimization problems, behave over this distribution. So maybe an instructive example is the independent set problem, right? What is the largest independent set of vertices where no two are adjacent in such a random graph? So using sort of fairly standard methods like first and second moment method kinds of things, it was shown a while ago how this scales if you consider the limit sort of first as n goes to infinity, right? Then for any fixed d, this will be some fraction of the total number of vertices that will belong to the largest independent set. And then you can pin down how that fraction scales as a function of d. And this turns out to be this 2 log d over d scaling. And this is, it's not trivial, but it's not too hard. But then if you ask about that fraction for finite d, let's say for random 3 regular cubic graphs or 4 regular, then the story becomes suddenly much more interesting and complicated. And here, this ties into the literature from statistical physics. So there are these kind of precise but non-rigorous predictions coming from that community about what this fraction is for a given d. This involves so-called the replica trick and replica symmetry breaking and things like that you might have come across. And this is known to be exactly correct, but only for sufficiently large degrees d. And for, let's say, this case of random 3 regular graphs, all we know is bounds on either side. We know that the typical fraction of vertices in a maximum independent set is at least something, and at most something else, but these don't match. So already here, kind of this is just emphasized that these are hard problems, and there is a lot of nuance even in just pinning down this true behavior without asking any computational questions yet. So what I'll be asking about is, okay, if we look at polynomial time certification algorithms, right, that take a graph and output a number that must be, let's say, a bound on the maximum independent set, how close can these get to the true value, kind of typically over this distribution? And in both of these situations I was talking about, in the case of the degree getting large, which is somewhat easier, you should think, and in the case of finite degree, which is harder. So usually when people have questions before, the kind of program for understanding computational hardness has been to try to prove that certain otherwise effective families of certification algorithms do not work. In particular, such algorithms come usually from convex relaxation. So a little later, I'll show some kind of ad hoc ideas that are simpler than this that work on a case-by-case basis. But usually these are formed by taking your problem and bounding it by a linear or semi-definite program, something like that. And kind of within this class, the sort of most powerful, at least at a course level, of these relaxations is the so-called sum of squares hierarchy of semi-definite programs. This gives a sequence of these programs that always give you an upper bound that you can solve at greater and greater cost, and that give you tighter and tighter bounds. Right? And so you can ask how far in this hierarchy, how expensive of a program do you have to solve to get a good bound? There's a proof technique that I won't get into called pseudo-calibration for proving lower bounds against this specific family of semi-definite programs in these kinds of random problems. And all I want to say about this is that it's kind of pretty clear to experts, not really myself, on this technique, that it runs into issues when you start asking about distributions like these random graphs that have sparsity, right, and that have strong correlations. And the distribution that we're asking about has both of these. So for example, if you asked similar questions for Erdos-Renyi random graphs, where you just flip a fair coin for every edge, that would be easier, right? That, if you imagine the graph as kind of a vector in edge space, that would be a dense vector, right, first of all, and its entries would be independent random variables. In our case, the graph sort of vector in edge space is a sparse random vector, and its entries are highly dependent because there can only be, 3 edges or whatever touching a given vertex, and if 3 of them are there already, then all the others kind of automatically must be 0 and things like that. And so from this point of view, at a technical level, figuring out how to make some kind of arguments about certification for these types of problems is an important technical challenge. So that's another motivation. So what I and various collaborators have explored is a different approach to kind of making arguments about computational hardness of these problems, which instead uses reductions. In particular, it uses reductions from statistics problems, particular statistics problems that we have other tools to sort of reason about. So here's the idea of how such an argument goes. So let's stick with this independent set problem. So we know, let's say for a random 3 regular graph, that the typical size of the independent set is some fraction. It's about kind of 0.45 times the number of vertices. This is the typical size of the largest independent set. So what I want to think about is hypothesis testing between two graph distributions. One is this uniformly random three regular graph. And another one, think of it as some version of that I've tampered with by inserting an unusually large independent set in some way. Right, so I'm going to kind of mess with it such that the largest independent set typically contains a larger fraction of the vertices. Right, and now imagine that we have a certification algorithm which proves upper bounds. Right, so on the one hand, on this planted distribution, the one where I've planted a large independent set, the value it outputs must be large because it always gives you a valid upper bound, right? And so, then the true value here is large. On the other hand, if it was kind of effective on the null distribution, the original one, then this would be an effective test statistic running this algorithm because its value would be small on uniformly random graphs and it would be large under these kind of tampered with random graphs. Right? And so in this way, we learn that if somehow we could argue that this hypothesis testing, distinguishing these two distributions problem is hard, right, then we would learn that certification is also hard. Kind of certifying that the largest independent set is no smaller, is any smaller than the typical value under this distribution. So this property of this testing problem being hard is something I'll refer to as an object being quietly planted. So kind of inserted into this distribution in a way that's quiet or hard to notice efficient for polynomial time algorithms. So I'll pause. I don't know if I'm supposed to pause, but this is a good time to pause if there are any questions.
So I have a question. I've heard from people that the planted click problem is supposed to be like absolutely impossible, and there's like a conjecture that like doing better than random chance is completely impossible. Like, is that something different than this, or is that?
No. So that's very related. That's exactly a problem kind of in this family. Except that talks about this, that problem is sort of better understood than the ones that I'll talk about because it involves putting an unusually large clique in an Erdős-Renyi random graph, right, which doesn't have those difficulties of sparsity and correlations and so on. And so for that, we can understand even directly these kind of powerful certification algorithms, sum of squares and so on. But at the level of the formulation of the problem, it's exactly the same kind of thing. That's right.
Okay, thanks.
Yep.
So with regards to this notion of planting, can you elaborate a little bit more? Like, I'm a little confused as to exactly what's going on. Like, you have a set of graphs and then, or you're just tweaking the distribution of where the edges connect. It's not entirely clear.
Yeah. So for now, I'm just using the word planting as kind of an evocative term, maybe confusing more than evocative. But so for now, I'm just talking about two distributions, right? So you're kind of, you want to make a statement about the distribution in green, the uniformly random graph, and I'm using the distribution in purple as a tool to make that statement, right? If I can prove a certain hardness result for distinguishing between these two things, then I will learn a hardness result about this certification problem that only has to do with the green distribution. But so, and we'll see a bunch of examples in a second. Ultimately, the way that we will construct these planted distributions, these distributions P, it could in principle be anything, but it will actually be by kind of sampling from the green distribution and then doing something to that sample, or maybe sort of changing, but only slightly, the kind of some parameters, let's say, in that distribution, something like that. So that's at an intuitive level how I would suggest thinking about it.
Okay, thank you.
Mm-hmm. Okay, let me continue. So let's, to clarify exactly that, talk about how these planting strategies have looked, and I'll kind of build up through a couple of previous works up to what Shifan and I came up with most recently. So we started out thinking about this with some other collaborators in the context of a different problem, which is kind of easier in that sense of avoiding sort of sparsity and correlations and so on. So we were interested in the following optimization problem: maximizing. It's kind of like a Gaussian version of max cut, right? So if you look at this maximization of a quadratic form over the hypercube, right? If W were a graph Laplacian, then this would exactly be max cut. But even that is a little bit kind of more complicated than we wanted to deal with. So we looked at the version of this with just an IID Gaussian random matrix in there instead. And this also has some motivation coming from statistical physics and so on, but that won't be important for us. Except that the statistical physics literature tells us that this is a very complicated optimization problem. It has this very sort of rich geometry of the optimization landscape. And there is a very kind of deep, also elaborate formula for what that true value of this optimization problem is. So it scales like n to the 3/2, which you can view as a factor of square root n from each of the x's, that those are their norms, and another factor of square root n from the norm of an IID Gaussian matrix. This is kind of from classic random matrix theory, right? But the constant in front of that n to the 3/2 is this kind of magic number, sometimes called the Parisi constant, which is a little bit bigger than 1.5. It's some number, but so all of this kind of deep work gives us this benchmark to compare certification algorithms against. On the other hand, people looked at some of these kind of semi-definite programming relaxations and so on, and even more sophisticated versions of these kinds of algorithms seemed to be stuck at the same performance as a very naive algorithm, which just forgets about the hypercube structure, which is what is granting this problem all of its complexity, and says, well, I'll just bound this kind of as though x were the top eigenvector of this matrix, in which case we get this bound, as I was saying, of n times the largest eigenvalue, and the largest eigenvalue in the scaling that I haven't written down precisely is like 2 times square root n. This is like the semicircle law from 2 to -2 in random matrix theory. And so it seems stuck at this, certification does, at this higher value, this higher constant in particular of 2 rather than 1.5. So we were trying to kind of account for this observation by this method of quiet planting. So how would you implement quiet planting for this distribution? So what do we want to do? We want to take W, this just purely random matrix, and somehow mess with it so that some hypercube vector has an exceptionally large quadratic form with that matrix. So a simple kind of naive approach is to say, well, I'll just pick some, so I don't want to do this kind of in a blatant, like obvious way to an algorithm. So maybe I should pick a random hypercube vector with which to increase the quadratic form. And then I'll just add this rank 1 kind of extra component to my random matrix. And I'll try to make this added amount so big that it increases the typical quadratic form. And so if you put this constant gamma here, like I've written, then you can show that the size that this makes that quadratic form have is roughly gamma times n to the 3/2. So if we want to use this plan to show that certification is hard, then we should take gamma to be approximately 2. Right? So this is what how we're hoping to use this strategy. Right? On the other hand, we also have to ask the question of, okay, is this actually a quiet way to hide a solution to this problem? So is it easy or is it hard for a testing algorithm to tell the difference between the green distribution and the purple one for W? Right? So in particular, a natural thing to look at is, can an algorithm tell the difference by looking at just the eigenvalues? And so here there's another kind of somewhat maybe well-known result of random matrix theory, which says that there is a transition in when this kind of perturbation creates an outlier eigenvalue, kind of something lying outside of the typical distribution. And this happens much before the size that we want to take gamma to. This happens once gamma is bigger than 1, right? And so we wanted to be able to take gamma equals 2 in this strategy, right? But all we can do is take gamma equals 1 if we want to hide a vector effectively. So this doesn't seem to work. And what this first try teaches us maybe is that when we construct these planted distributions, then in particular the eigenvalues, if we're looking at these kind of matrix problems, the eigenvalues should kind of not give away that we've messed with the distribution in some way. So with that intuition, we came up with a different idea, which was to say, okay, well, if it's the eigenvalues that are causing problems, then we just won't touch them at all. We'll just draw this IID Gaussian matrix, and so here I'm talking about symmetric Gaussian matrices, like from the Gaussian orthogonal ensemble or whatever, so I can talk about kind of eigenvalues and real eigenvectors. So I'll leave the eigenvalues the same, and I will just rotate the eigenvectors, the eigenspaces, so that the ones with largest eigenvalue are close to aligned with some particular hypercube vector. So a priori, you can show that, like, let's say the top n over 100 or something eigenvectors, they span a uniformly random subspace. And instead of that, I'm going to pick some hypercube vector, and I'm going to rotate that subspace such that it aligns unusually well with that vector, right? So the kind of value that I'll plant then is this typical largest eigenvalue, which again scales like 2 times square root n, right? And everything gets scaled by n because we're talking about the hypercube where vectors have norm square root n. Right, so this achieves this constant of 2 that we wanted. And then using some other tools, we sort of formulated and gave some evidence for this conjecture, that it's hard to hypothesis test between these two different random subspaces. A low-dimensional subspace that's uniformly random, and a low-dimensional subspace that has been rotated. So here there's some actual, description of this rotation. I'm kind of speaking a little bit informally, but that's kind of biased towards a uniformly random hypercube vector. And this is always hard for any fraction of the dimension. So long as the dimension is kind of macroscopic, it's some positive fraction of the total. For any kind of slightly less than total kind of containment of a hypercube vector, so let's say containing some large fraction of the L2 mass, we can give evidence that this kind of problem is always hard. And so this is always a quiet planting. And so what we learn from this, right, is that it's hard to certify bounds on this optimization problem that are any smaller than the typical value of just a very naive spectral bound, where we forget about all of the hypercube structure. And actually, this whole story is not really specific to the hypercube, and we could show that for a pretty large family of other kind of constrained, we called it constrained PCA, kind of constrained eigenvalue types of problems. The best you can do for certification is just forget that you have any constraints and bound it as though it were a full eigenvalue problem. So this is one example of how this kind of story plays out, right? Here's a summary of what we learned from this, right? So there's some true value of an optimization problem. There's some kind of naive bound, right? And we can certify up to that naive bound, but there's some kind of large interval between that and the truth where we can't certify, at least it seems like. But this maybe seems kind of far from the setting that I started out talking about, right? Because we were talking about graphs and sparse random graphs, and here I'm talking about dense, just random matrices. So let's kind of gradually make our way towards these graph problems. So that problem, as I was saying, looks kind of like max cut. It's this kind of Gaussianized max cut. So we started thinking about, okay, what does this teach us about trying to do the same thing for max cut over random regular graphs? So here, the whole story is sort of similar, but gets a little bit more complicated. And in fact, this problem is directly related to that Gaussian problem. So for example, if you look at how the true value of this scales, so here, dn over 2 is the total number of edges a deregular graph on n vertices. So this is saying that the max cut is some fraction of the total number of edges, like it was some fraction of the number of vertices for independent set. So 1/2 is you can show the fraction of edges you would cut if you picked a random subset, a random partition for max cut. That's the kind of expected number. So that's sort of the trivial value, and then this formula is expressing some gain over that. And the remarkable thing that these folks could show is that actually it's that same magic constant, that Parisi number, that shows up in the behavior of the max cut of random regular graphs. And there is some further scaling, so it's some kind of small improvement, this order 1/√d in the fraction of edges that you can make over just a purely random cut. So this is just the true value. This is like what used to be 1.5 n to the 3/2. This plays the role of that for this problem. And like we had a kind of naive spectral bound before, there's a similar sort of benchmark certification algorithm here, which people might have seen. This is the so-called Hoffman bound on the max cut. So there are versions of the Hoffman bound for different things, for independent set and chromatic number, and also for max cut and these kind of partitioning problems. So it gives you some way to bound the max cut in terms of the eigenvalues of a graph. And this is phrased specifically for deregular graphs. Right? And the value looks like this. Again, it's of the form the number of edges times something a little bit bigger than 1/2. Now we know what the eigenvalues of random regular graphs look like, so we can sort of plug that in and get a similar looking expression. And again, it up to some, kind of the structure of these formulas, the issue is exactly the same, that in the truth, there's this kind of magic constant 1.5, and in our benchmark bound, that is replaced by 2. So our benchmark bound is kind of separated at the level of these constants from the truth. And so people thought, so in this paper sort of indirectly, but essentially we're thinking about how to construct planting that would witness this fact, this gap. And again, they chose this kind of naive strategy of saying, well, we want to pick a random graph, a random regular graph that has an unusually large cut. So we'll just pick a cut at random. We'll partition the edges, the vertices into 2 groups. And then we'll pick a random regular graph sort of conditional on some particular number of edges crossing that cut that you can regulate in terms of this constant beta and this constant eta. And again, this has the same exact issue in terms of these constants, where you can show that this is only quiet, and for reasons to do with looking at the eigenvalues of a graph, up to eta scaling like 1 rather than 2 over something. So I don't want to get too far into this, but the interesting thing that I want to draw your attention to is that there is a way to fix this issue we did with rotating eigenspaces, but that looks completely different from rotating the eigenspaces for the case of this problem. So here what we do is, instead of doing what I just said with fixing a cut and fixing the total number of edges that go across that cut, what we do is we apply a kind of more rigid constraint, a constraint around every vertex. Instead of controlling the total number of edges going across, we say actually every vertex has to have the same number of edges going across, same number of edges staying inside its part of the partition, or its quote unquote community. Right? And so this kind of solves the problem, and it improves this constant from 1 to 2. And again, we learn as a kind of application that this spectral Hoffman bound is an optimal certificate for max cut on random regular graphs. So to summarize again, right, we get this kind of picture, which is the same exact thing that we had before, only the formulas got more complicated. But even at the level of the constants that show up and the difference between 1.5 and 2, this is a totally analogous story. Okay. Let me just illustrate for a second, right, the difference between these 2 planting strategies for graphs. So the first one, right, about the total number of edges crossing, was about fixing this partition into, let's say, blue and green, right? And then just fixing the number of edges that are in the kind of dark gray part here. And so in particular, if we look at local neighborhoods of vertices, we don't kind of have any control over them, right? So the blue vertex on the bottom has one neighbor in its own group, in its own kind of part, and all the others in the other one, and the green one on top has two in its own, and the other five in the other. Right. We also looked at similar things for partitions into multiple subsets, where there is an even more kind of pronounced version of this, right, where you can have all kinds of different distributions of how your neighbors are distributed among the other, let's say, in this case, the other three, or your one group and the other three, and things like that. So this is like a K-cut or multi-section, sometimes people call it, problem. Right. On the other hand, this equitable planting strategy forces each vertex to have exactly the same number of neighbors, kind of the same pattern, the same number of neighbors in its own part and in the other one for the case of two parts. Right. And similarly, in each the same, so a particular number of vertices in its own part, and then the same equal number in each of the others in this larger number of parts variant of max cut. And the main message that I'm going to try to kind of elaborate on in the rest of the talk is that what is making this work is that for some reason, which should not yet be clear at all, this planting strategy really does do some graph-valued version of keeping the eigenvalues but manipulating the eigenspaces of a matrix. Right, which maybe I should have emphasized. You can't do that to graphs, right? You can't just take an adjacency matrix or a Laplacian or something and rotate around its eigenspaces because you won't stay in kind of graph space, right? So this is all to deal with that constraint. Okay, so before I get into justifying this, any questions maybe? Okay, then I will continue. So instead of explaining that particular way of inserting some kind of structure in a graph kind of on its own, I'll introduce now the family of strategies that Shifan and I looked at, which have to do with constructing random lifts of graphs. So what is this? It kind of constructs it's a family of distributions of random regular graphs, which are based on a fixed template deregular graph. So I start with some particular h, let's say this 3 regular graph, right? And using it, I'm going to construct a larger random regular graph that no longer will have the uniform distribution. So how do I do this? I replace each vertex with a bunch of vertices, let's say 4 in this case, and I look at each edge of this graph, and for each edge in H, I put in a uniformly randomly chosen uniformly at random matching between those two collections of vertices, right? So for this top edge, I put in some random matching, so a random kind of permutation there, and then I repeat it for each edge in H. So you can check that this operation, if I start with a deregular graph, I'll end up with a deregular graph, right? Because each vertex will participate in exactly D of these matchings. But now, so H is just deterministic. It's some fixed thing that's specifying this procedure. And the graph on the right will be random. But as we'll see, it will kind of inherit some of the properties of H. And that gives us this sort of steerable family of random regular graphs to work with. So to return for a second to the model I was talking about before, it is a simple special case of this. So I didn't mention, but if I have a loop, right, I can interpret that as putting a matching inside of one of those blobs. And that again will keep this, will preserve the degree. Right? So then you can convince yourself that this equitable planting model is just a random lift of this kind of barbell graph on 2 vertices, right? Because what will happen, well, each loop will give a vertex a random neighbor in its own subset, right? And each edge going across will give it exactly one neighbor in the other subset, in the other part of the partition. And so this is a different way of expressing the same distribution. So we saw before, right, that to understand when these planting strategies are quiet or not, it's important to look at the eigenvalues. And fortunately, there's this kind of sophisticated recent work really in random matrix theory and kind of free probability that tells us exactly how large random lifts of a particular base graph H look as this kind of factor by which we're lifting, the factor by which we're, the number of vertices in each of the blobs in my picture, as that goes to infinity, but as the base graph is fixed. So you can check that any lift, regardless of whether it's random or whether you pick some particular matchings, it inherits all of the eigenvalues of the base graph of H. So if you pick an eigenpair, if you kind of lift up that eigenvector to a vector kind of valued on the vertices of the lifted graph by making it constant on each blob, then you'll get an eigenvector with the same eigenvalue, right? So every eigenvalue of H is always going to be an eigenvalue in the lift. And so it remains, if you want to understand the eigenvalues of random lifts, to say what else is there, right? And they give this beautiful answer that actually the spectrum of a random lift looks like the superposition of two things, of these eigenvalues that have to be there, right? These individual ones I've drawn here, which are the spectrum of the base graph, and what the spectrum would look like if the graph were just a uniformly random regular graph. So we'll talk about this distribution in a second, but this is known kind of analytically at some particular shape. So the question for us, right, is when does that look indistinguishable from just the second part, from just the spectrum of a uniformly random regular graph? And this makes it easy to answer that question because, of course, it's just when there are no outlier eigenvalues, right? It's just when this big shape kind of swallows up all of the eigenvalues that look that are outside of some particular interval, which is where that distribution is supported. So to understand kind of quantitatively what that means, we need to know what that distribution is. This is the so-called Keston-McKay distribution. This is another kind of old random matrix theory result, that this is the limiting distribution of the adjacency matrix of a random regular graph of a particular degree, right? And it has this interval that it's supported on, whose endpoints are between minus 2 square root d minus 1 and 2 square root d minus 1, which might be a kind of familiar number to some in the audience. In particular, right, a graph whose eigenvalues lie inside this interval, which is exactly the criterion for H, for us generating a quiet planting. This is exactly the definition of a Ramanujan graph, right, which comes up in the study of expanders and all of that. And this interval, this property, is kind of as compact in some sense as the spectrum of any d-regular graph can be, as kind of small as it can possibly be, which is why this is important for expansion and so forth. And so the conjecture that we propose, based on this and some other evidence I'll mention in a second, is that if you pick a Ramanujan d-regular base graph, then it's hard to distinguish a large random lift of that from a uniformly random d-regular graph on the same number of vertices. So that can't quite be true because of something I just said earlier, because these lifts inherit some specific eigenvalues. So even if the eigenvalue, like let's say 2 is an eigenvalue of H, right? 2 will always be an eigenvalue of a random lift. And I said, well, 2 might be kind of swallowed up in this big bulk of eigenvalues, but you can still calculate them and you can look to see, or you can do something with the characteristic polynomial or something, right? And you can check, or a determinant, you can check whether 2 is an eigenvalue of a graph, right, efficiently. So we have to adjust this a little bit. And the real conjecture that we make is if you start with this random lift and then you add a little bit of noise. So it's a little tricky to say what it means to add noise to a regular graph because you have to maintain the regularity, but you can do a certain kind of edge swapping operation. So if you do a small number of those, then because this having specific kind of bulk eigenvalues in the middle of all of them rather than extreme eigenvalues is kind of a fragile property of a graph or really a matrix, right, fragile to sort of perturbations, this will sort of mess them up, we believe, and these two distributions should be hard to distinguish. Now, the evidence for this so far maybe seems a little bit flimsy, right, because it's just on the basis of looking at the eigenvalues. And so to sort of shore this up a little bit more, we looked at something like that plays the role, or maybe ought to play the role of the sum of squares hierarchy, which people think a lot about for optimization and certification problems, but kind of an analogous hierarchy for hypothesis testing problems, which is what we're talking about now, right? So this is this so-called local statistics hierarchy, which is increasingly studied, but hasn't kind of massively caught on, but is a very natural family of semi-definite programs for trying to solve these problems. And we can give lower bounds against this kind of much more powerful family of testing algorithms also, saying that this problem that we propose is hard. Okay, so the last thing that I want to talk about is some applications of this to deriving some particular lower bounds, some claims that some certification problems are hard. And we'll see that this really gives us some powerful machinery for doing that. So why is that? Well, there is this proof technique that really boils this conjecture kind of gives us that really makes this task pretty simple. So let's say, and we'll see that some functions that we're interested in have this property, let's say we have a function that is monotone in one direction or the other, undertaking lifts. So if we take a lift of a graph, right, then this function gets no bigger or no smaller. So for example, you can check that this is the case for a normalized version of independent set, the fraction of edges in the maximum independent set. Because if I have an independent set in H in my little base graph before, if you look at all of the blobs that an independent set lifts to, they must also have no adjacent pairs, right? Because there's nowhere for those edges to come from, because they only come from edges in H. Right? And so the claim is that if you're interested in certification, so certifying bounds on such a function, and you have some Ramanujan graph, then the value of the function on that graph is gives you a negative result about certification. It's hard to certify beyond the value of that graph. And this is just because, such a graph gives you this quiet planting strategy. And if you work through the details, you'll see that that exactly proves, conditional on this conjecture, that it's hard to certify lower than, let's say, f of h, right? A value lower than f of h. So the bottom line, right, is that if we are looking for this threshold, like kind of up to where is certification possible, right, this gives us a lower bound on it, which is this weird and fascinating optimization problem, which is what is the maximum over all Ramanujan graphs of your function? Let's say, what is the biggest possible fraction of vertices in the maximum independence of a Ramanujan, deregular, 3-regular graph, something like that. So those problems seem very hard to address. But even if we even if we can't do that, it's enough to prove a lower bound to just kind of produce one Ramanujan graph, right, and check that it has some properties. So it's really this sort of proof by example thing that it allows us to do. So let me go quickly through some examples. One simple case is the dominating set problem. So a dominating set is a set of vertices such that every vertex of your graph is either in the set or is adjacent to some vertex in the set, right? So it kind of, the graph is covered by stars at those vertices. And so here you're interested in the opposite thing. It's a minimization rather than maximization problem. And again, to get this kind of monotonicity, you need to normalize this to view it as a fraction of the number of vertices in the graph. So the true value of this fraction understood for large degrees, again, a while ago to be this log d over d quantity. And we can compare this to a simple certification algorithm, which just says, well, if I'm constructing one of these dominating sets, each vertex in there can kind of take care of at most d plus 1 vertices. It's kind of a volumetric argument if you want, right? It can take care of itself and its d neighbors. So the fraction must be at least 1 over d plus 1. And we can show that conditional on this conjecture, no polynomial time algorithm can improve on this for any d by any positive amount. And really the interesting thing is that the proof is super simple. So first you just check that there's this lift monotonicity under lifts property. And then you just need to produce a Ramanujan deregular graph with a small dominating set. So you can check that the complete graph on d plus 1 vertices, this is a deregular graph, you can check that it's Ramanujan, right? And this kind of normalized domination number of it is exactly 1 over d plus 1, because any one vertex is a dominating set of this graph. And that's it, right? That's all you need to do. So let me return to one of the examples I was talking about before of independent set. So here again, you have to kind of work with this normalized version, the fraction of vertices in the maximum independent set, right? We saw this result about the true value. So actually, let me just go back for a second if I can. So here, right, another thing to emphasize maybe is that there's this gap again, right? I didn't draw the picture, but the best possible certificate in this case is much smaller than the true value by this factor of log d. Right, so here again, for independent set, there's this true value of 2 log d over d that I mentioned before. And there's a benchmark spectral algorithm, kind of like for max cut, again, in this Hoffman family of bounds, which gives you some formula in terms of the eigenvalues. You can plug in that information about the Keston-McKay distribution, and you get that this scales as 2 over square root d, right, which is much bigger than roughly 1 over d, basically, right, log d over d. And what we can show is that if you look at the limit as d goes to infinity, again, this is optimal. And now the proof just requires a slightly more flexible kind of family of Ramanujan graphs to look at, which are not just the complete graph, but the complete graph where you replace each edge with a bunch of parallel edges with the same number. And you kind of look at when is this Ramanujan, you optimize over that family, and this result falls out. But things get a little more interesting, right? If we start looking at finite d, so let's say for random 4 regular graphs, for example. So as I was saying, here we don't know what the true value is. We know that it falls in a particular interval, right? This fraction of vertices in the maximum independent set. And we can calculate what the typical fraction is that this spectral bound gives us, and it's bigger, right? It's outside of that interval. And we can show a lower bound that says that you can't go below another particular number, which is also outside the interval. So I'll draw a picture of this that might make a little more sense in a second. But the nice thing is that the proof is really just a graph. Like here's a graph. You can calculate its eigenvalues in MATLAB or NumPy or whatever. It's a Ramanujan graph. You can check that it has a big independent set, and that's it. Right. So we get this kind of more nuanced version of the picture from before, where we don't even know what the true value is. We just know that it falls in a particular interval, right? And yet we can show that there is definitely a region, a kind of a hardness phenomenon for certification over this distribution, right? There's some region where it's hard to certify bounds of that value, which includes the true value. And we actually don't know in this case whether we expect this spectral Hoffman bound to be optimal or not, the way other spectral bounds were. We probably expect it actually not to be, but that's a different, separate story. And just to show you that this approach can go further, so I won't go into the details, but this is some big Ramanujan 7 regular graph. They're actually small Ramanujan graphs are not that hard to find, right? The big open problem is about finding these infinite sequences of them, but you can find small ones just on the computer with various heuristics. And so using this, we can give a similar result for the chromatic number. And again, finding this just by computer search. Right, and so for all of these problems that I mentioned earlier, we can get similar results, either showing that something, some spectral type of bound or some naive bound is optimal, or showing that you can't, at least that you can't kind of certify down to the true value for certain problems with the specific values of the degree. So let me wrap up quickly. So one interesting thing is that really this approach is not necessarily specific to certification, but really can be used to try to say something about any class of algorithms that makes some guarantees over lots of instances, right? So you can argue if you could use the output of an algorithm to solve this kind of hypothesis testing problem, then in principle you can use this quiet planting plan to show some kind of hardness result for some class of computations. So I managed to do this in some other work for certain sampling problems where there's an interesting kind of issue about how do you even view sampling as outputting a real number, and this is by this so-called equivalence or reduction between sampling and counting and approximating partition functions and so on. But other things that we don't know how to do are to use this to, let's say something about the other side of computational problems from my very first slide, not certification, but kind of search or just standard optimization, like finding a good cut, a large cut in a graph. Or for approximation algorithms that make kind of guarantees on the approximation ratio. In particular, I think a nice concrete question is whether this can give some evidence that, let's say, the Gomans-Williamson approximation algorithm is optimal for max cut. So currently, the evidence that we have for this is related to the unique games conjecture, right? Whereas this, constructing these kind of distributions that are hard to distinguish, but that a better approximation algorithm would distinguish, is a completely different sort of style of plan for giving evidence for that hardness. So finally, would just to give kind of a couple of extra open problems. As I was saying, at a technical level, we really don't know how to do lots of the kinds of kind of calculations and proofs that we like to do with random regular graphs. So understanding how this distribution interacts with sum of squares or low degree polynomial algorithms that some people might have heard of is, I think, an interesting, important challenge. This idea also, I think, gives kind of new motivation to a topic that people studied when random lifts were first introduced, but then that kind of fell off, which is to ask questions like, as a function of h, what is the typical size of the maximum independent set in a large random lift of h? Or what is the max cut? All of these kinds of things. So there are actually some interesting kind of phenomena, some dependence on kind of the structure of h that is totally incompletely understood that seems to be important for answering the kinds of questions that this raises. And finally, the most sort of absurd of the problems, I think, is to try to say anything at all about these problems like what is the largest possible independent set, let's say in a 3 regular Ramanujan graph, or even D regular for a large D. How do we understand these optimizations over Ramanujan graphs that this whole proof technique suggests that we look at? And we really have no idea how to make any claims aside from just looking for Ramanujan graphs on the computer. But you know, perhaps you could come up with a dual problem that kind of bounds this from the other side and so on. But this is an interesting direction that I'd be happy to chat about with anyone who's interested. All right, thanks for your attention. Happy to answer other questions.
All right, so I'm going to thank the speaker by clicking a button. I encourage the rest of the audience to do the same. We'll stop the recording here.